Welcome to your first set of Edpuzzle notes. So we're going to be going over the periodic table, and these notes are going to be on page 42 in your notebook. As I go along, please write down the notes, but feel free to pause the video at any time so that you can catch up on writing in the notes, and rewind anytime you want to hear something again. So here's a quick overview of what we'll talk about. We're going to start out by talking about the periodic table. That'll be the first slide that I show you. Then we're going to talk about groups and periods. Then we'll talk about the octet rule. That'll be the third slide. And then finally, electron dot diagrams will be the last thing that we do. Okay, here we go. Our question for the top of page 42 is, what do elements in the same group have in common? So you'll need to write the answer to this question at the top of page 43. These notes are called the periodic table. Our first vocabulary term is periodic table. A periodic table is the table where elements are organized by increasing atomic number. And remember that atomic number refers to our number of protons. In the late 1800s, Dmitri Mendeleev devised the first periodic table based on atomic mass. However, some elements were out of order. In 1912, Henry G.J. Moseley arranged elements by atomic number, and this is what we have today. So this top picture is Mr. Mendeleev, and he has this periodic table, which is pretty weird looking. Let me zoom in on it for you. Look at that. So he's still listing hydrogen as the very first one, and then he's got lithium down here, but he's got these different little columns. So really, if you want to understand what this periodic table is supposed to look like, or see how it's related to the one that we use now, try turning it this way, and you'll start to see, oh hey, so here's hydrogen, and then you've got lithium and sodium and potassium and rubidium, who all have things in common, and cesium. But wait, francium's not in the right spot, because those were all elements that we saw today react with water. And so they should all be in the same spot, but they're not. And so we're kind of like we were before, but not exactly. So let me turn this back the way that it was. Whoop. Here we go. And then here's Moseley's periodic table, this is the one that we're all familiar with. So he's got everything in the columns, in the rows, the way we know it. These little groups you are familiar with already. So this is much more what we are used to seeing. He actually was looking at Mendeleev's periodic table and thought, well, some of these aren't quite in the right order, but if I actually switch them around and arrange them in order of atomic number instead of their atomic mass, so just by protons instead of protons and neutrons, then I can actually fix those errors in the order. And so that's exactly what he did, and that is what we see today. Okay, our next slide is going to go into the groups and periods on the periodic table. So groups refers to the vertical columns of elements, and they all have similar properties, like the alkali metals that we saw today, the sodium that blew up when it hit the water. All of those other elements that are in that same first group have similar properties. So that property that it blows up when it's in water, we know that that is a chemical property. But they also have some similar physical properties, like those alkali metals that are in that first column. They're all really soft, but they're shiny. They'll react with the air. Well, that's a chemical property, actually. But the soft and shiny, those are physical properties. So it's not just chemical, but it's also physical properties, both of those. Those groups are numbered 1 through 18 all the way across the periodic table. Elements that are in the same group have the same number of electrons in their outer energy shell. This is actually one of the reasons that we've discovered why they have similar properties. So the fact that they have the same number of electrons in their outer energy level allows them to bond in certain ways. Our next chapter goes more into bonding. These electrons that are in this outer energy level are called valence electrons. So valence electrons are in the outer energy level, or sometimes it's actually called the valence energy level or the valence shell. The number of valence electrons is equal to the group number, and I'm going to show you a picture that shows this in a second. Periods are the horizontal rows of elements containing an increasing number of protons and electrons, and periods are numbered 1 through 7. So each of the rows, as we go across, those are numbered 1 through 7. Elements have the same number of energy levels, aka electron shells, as their period number. Each row in the periodic table ends when an outer energy level is filled. Now let me show you what these actually mean on the periodic table. Okay, this is kind of a condensed version of the periodic table. Notice that we've taken the groups that have boron and aluminum that are actually way over on the other side of the periodic table. Our periodic table normally looks like this. But we've actually taken the transition metals out of this picture. And so we're getting this mini version of the periodic table. So we've just taken out the transition elements, so that's why it looks weird here. And we're also just going through the first 3 rows. Yep, wait, that was wrong, sorry. So we're just going through the first 3 rows. 1, 2, 3, or the first 3 periods in this picture. So what I want you to notice in this picture is that in row 1, both of these, hydrogen and helium, only have 1 shell of electrons. Their valence shell is their one and only shell. So this one has 1 and this one has 2. Then in the second row, all of these have 2 shells, 1, 2, or 1 where the black ones are, and then 2 where the valence electrons are. Notice all of the valence electrons are shown in red. So all of these have just 2 rings of electrons. In our third row, or our third period, we have 1, 2, 3 shells of electrons. And so these valence electrons are still on the outermost ring, so they're on that third ring out. Now the number of valence electrons is going to be shown by this number. And on our periodic table, the transition elements are usually, their numbers are still, like this is still 3, but it's called 3b. And then you have 4b, 5b, 6b, 7b, 8b, 9b, all the way over to this side. And then it starts with the A's again. So this is actually 3A, then 4A, 5A, 6A, 7A, and then the last one is 8A. So that's what's going on here with these A's and B's. This is also technically known as 18, 17, 16, 15, 15, 14, and 13. 1 and 2 are always just 1 and 2 because they're before the transition elements start. So the transition ones would be right in here. Okay. And so notice that the number of valence electrons, the number of little red dots on that outermost circle, always match up this number here. So all of these have 1 valence electron. All of these have 2 valence electrons. These all have 3. And then this one is the one that's kind of weird. In this one, helium has 2. And that's just because in that first shell, you can only have 2. And in this shell, you can have up to 8. So it's okay for this one to be all the way up to 8. This one, since helium is so much smaller, it only has 2 protons, so it only needs 2 electrons. It's happy just having those 2. It doesn't need to have a full 8. Okay, next. So this is the octet rule, and you'll want to add this on to your notes as well. This is going to go into your notes. Each of the 7 energy levels can hold a maximum number of electrons. So you can see the table that you made on page 36 in order to see those energy levels and the maximum number of electrons they can hold. However, the outer layer can only hold 8 electrons. This is called the octet rule. So I had you guys make this little table, and I really am sorry, but that's only partly true. The third layer can hold up to 18, but only if there's a 4th layer outside of it. So argon here has 3 layers, but its outermost layer is only going to hold 8 electrons. Down here, when these guys get up to 4 layers, then that 3rd layer could hold up to 18 electrons, but not necessary. So it has to have that outer layer first. Okay, the transition metals are going to be the ones where you're really going to see a lot of that up to 18 stuff happening, all of these things. They don't have as nice an order of valence electrons as these guys do. So these are a lot more confusing and complicated, and we don't need to deal with them. So, we just want to deal with these ones here. So this actually just lists for you the number of valence electrons in each of these elements, in our main group elements. So all of the ones in the first column, 1, second column, 2, 3, 4, and then this last column is the weird one because of this guy right here. Remember, this one is helium. Helium only has 2 protons. It only needs 2 electrons, so it's only going to have 2 in its valence shell anyway. And since it only has 1 shell, because it's in the first row, it's only going to fill up that first shell, and it can only hold 2. So this is the only element that does not go with that whole octet rule thing. This is the only one that's weird. So now we're going to draw some electron dot diagrams, and there's actually another term that is often used for electron dot diagrams. It's called Lewis dot structures. So would you guys, when you write this note, that electron dot diagrams use the element symbol and dots to represent the valence electrons of an atom, would you please also write that this is also known as Lewis dot structure. So that's just another name for an electron dot diagram. So what we're going to do is we are going to draw 4 electron dot diagrams. We're going to draw them for helium, oxygen, neon, and aluminum. First we're going to do helium. So on your periodic table, so you can pull the one out of, flip back in your notebook and find it, please locate helium and then try to figure out how many electrons helium needs to have. Well, remember, helium is the one that doesn't follow the octet rule. It or doesn't follow the rule about what column it's in or what group it's in. It only has 2 valence electrons. So what we need are the element symbol, which is He for helium. And then we just need to draw 2 dots. And we're going to draw them starting from the top and go clockwise. So 1 and 2. And that's helium. The next one we're going to do is oxygen. So please find oxygen on the periodic table. Oxygen's symbol is an O. just a capital O. And it does need to be capitalized, please. And the H in helium also needs to be capitalized, please. The E in helium should be lowercase. So now we're going to add on the valence electrons for oxygen. Oxygen has 6 protons, so it needs to have 6 electrons. But also notice that since it's in group 6, we automatically know that it will have 6 valence electrons. Oh, I did not do this the way that I just told you to do it. Remember, you should start at the top and then work your way around clockwise. So you would start here 1, then 2, 3, 4, 5, 6. Or you can do it the way that I did if you can plan that out in your head in advance, which you probably can. The next one that we'll do is neon. So please find neon on your periodic table. Neon has the symbol Ne, and since it's in the 8th group, we know it's going to have all 8 of these dots filled up. So notice that when it's full, we have 2 dots on all 4 sides of the letters. So there's neon. The last one that we're going to do is aluminum. So please find aluminum on your periodic table. Aluminum's symbol is Al. And aluminum has 3 valence electrons, just like that. Now sometimes it's actually pretty common to see aluminum written like this instead, without putting the dot on the bottom. There's no real rhyme or reason to which way you should do it, if you should do it this way or if you should do it this way. It doesn't really matter, but sometimes you'll see it drawn like this because putting it on the bottom all by itself seems weird, but I don't really think it's that weird. I don't know. I don't care if you write it this way or this way. It doesn't matter. So anything that you find in that 3rd group, if you write it like this or like this, I don't care. Either way is fine. Okay, so that's all of our notes for today, but there is one more picture that I want to show you. So this picture actually shows the Lewis dot structures for all of these main group elements. So notice that all of the ones in our first group, just the letters and then 1 dot out to the side. So that's actually very common for them, instead of to start up here, to actually start them on the side here, because it kind of seems a little weird, I guess, to have the dot on the top. So another one, these guys, notice I did mine on top and then on the side, and they're actually doing them on either side. That's fine too. Top and side is okay. On either side is okay. It's kind of like you're trying to spread them out as much as you can. And then notice these are all done the second way that I showed you. You could do 1, 2, 3 and have that 3rd one on the bottom instead of back here. You could have it down here. That would be okay. These are easy. You want one on all 4 sides for group 4. For group 5, they added an extra one up here. You could add it out on the side here. That's fine. These, notice they're adding the extra one over here instead of over here, which is also fine. Mainly, you just want to try to spread them out so that there's a maximum of 2 on each side, and you want to fill up all 4 sides before you double up. So these are Lewis dot structures for all of our main group elements, and just make sure that you've got all of the notes down that you need for that page, everything that we've gone over that I've asked you to write down, all of the green writing, and that's all you need to do, and I will see you in class next time. Thanks.